My name is Yoav Kessler. I'm from Tel Aviv University, Israel. And today I'll be talking about a novel sensing technique. In particular, I'll guide you through an interesting investigation of its response to different flow direction. Okay? So that's the overview of our talk. We'll start by introducing some flow sensors, some existing flow sensors and their need in the industry and academia. Then we'll show our sensing device, followed by model experiments, and finish by comparing between the both. We'll also summarize all and conclude about the feasibility and applicability of the sensing device. The ability to accurately quantify flow characteristics in a minimally invasive way is crucial in many engineering systems, such as flow controlling pipelines, aerodynamics, turbines, and the list goes on and on. Most of the MEMS-based flow sensors are follow either the mechanical or the thermal operational principle. In this flowchart, the two operational principles are further classified. Despite the tremendous body of research devoted to the miniaturization of these devices, there is still a gap expressed in the interplay between cost, low footprint, and complexity of the device and of its use. We propose a flow sensing device that is based on the combination between the mechanical and the thermal operational principle. So the most basic sensing block of our sensor is a double clamped beam that can buckle. By imposing electrical current through the single crystal silicon, material, it heats up due to Joule heating. Because of the double clamp configuration, the thermal expansion is limited, and the thermal energy translates into axial stress. At a certain temperature, the beam gives up, and the static buckling occurs. So, as you might understand, flow has crucial effect over this response. Measuring the flow using this device includes registering the critical current of the buckling or by monitoring the post-buckling deflection. We believe that in order to improve the sensitivity of flow sensors, one must find and exploit the nonlinearity between flow and the measured quantity. Our goal was to develop a theoretical and experimental framework for a new generation of sensors that exploit the nonlinearity of the static buckling. And we are going to talk about it in more detail in a few minutes. Most of the flow sensing devices, the ones that are already existing, are very complex. Simplicity was very important for our feasibility demonstration. In addition, the basic sensing block, the double clamped beam, has versatile modes of operation, as it can sense the velocity in the free flow or wall shear stress if installed on the wall. Either way, it can sense flow in different directions. In this work, we will concentrate in the parallel and perpendicular flow directions. So, we start by investigating the feasibility of this sensing technique using the model. We will start with the heat transfer equation. So, theta, which is, here's the cup and this is the theta, is the temperature excess above the ambient. We calculate it using the most common one-dimensional heat transfer equation. We neglect all terms of cooling mechanism except for the convection, that is this fellow, and the conduction within the material. By imposing the boundary conditions of ambient temperature at the anchors, we were able to find theta, and then we just integrated in order to find the average temperature axis above the ambient along the beam. So you must be wondering where the flow velocity is. So we consider two types of convective cooling. The first is natural convective at zero flow, and the second is the forced convection in the case of flow over the device. If you look closely, you'll find the flow velocity within the Reynolds number at the convection coefficient. So let's move on to the mechanical equation. The beam is described in the Kirchhoff model by using a reduced order model of Galerkin decomposition. We were able to calculate the midpoint deflection Wm, the temperature heights within the axial thermal strain, and here we have an additional effect, the drag force, that is also proportional to the square of the velocity. So, according to Emin and Naife, there is a better analytical way to solve the mechanical equation to find the midpoint deflection. We use this term in the case of the parallel flow, where there is no drag force. Okay, so before we set sail to the result of the simulation, we would like to describe the plot as we're about to show them. So each plot includes the buckling curve, namely the electrical current, as function of the midpoint deflection. Each color represents a constant flow velocity, also stated down here. We also include two insets presenting the post-buckling deflection at a constant current above the critical force and the critical current for different flow velocity. So in this case that we see now on the board is the natural convection case. At a certain current, the beam buckles and the deflection sharply changes from 0 to a post-buckle deflection. This sharp change, this sharp increase implies on very high sensitivity, as also reflected from the derivative of this kind of graph. So in the case of, and now we're going to split to the parallel investigation, and later we'll show the perpendicular one. So in the parallel investigation, due to the cooling by the convection, a higher current is required to reach to the critical buckling temperature. Accordingly, the post-buckling deflection decreases with the flow velocity. We notice that for faster flows, the static buckling behavior remains, and the trends are consistent. Of course, in opposed to the perpendicular one. So, in this case, in the perpendicular one, in the perpendicular flow the investigation of the perpendicular flow, we see that the steep increase in the response at buckling disappears, and a much smoother response is observed. Of course, this thing is unfortunate in terms of sensitivity. We also see that the deflection increase with the flow velocity until a certain temperature from which the convective cooling is more dominant. We attribute this effect to the competing interplay between the drag force increasing the response and the convective cooling leading to the decrease in the response. So let's move on and see the experiments. So this is a scheme of our experimental setup. Beams of various geometries were mounted on a chuck of a wafer prober. The voltage was supplied through a signal generator that generated a quasi-static triangular wave, quasi-static with respect to the period of the free vibration, as well as the heat transfer constant. The response of the beam were recorded using a video camera, and these videos were later processed using an image processing custom-made code. Dry air was supplied using a straight needle. This is some of the live show of the results. So let's move on to the results. And here we show the parallel results, okay, the parallel investigation. We compare between the model and the experiment. So as we can see, the results are qualitatively similar. The quantitative discrepancies are attributed to the effect that were neglected from our model, as well as some provocational uncertainties, such as geometrical and residual stress, etc. Moving on to the perpendicular investigation, so we notice that the response is quite different than the parallel one. This implies that measuring the direction of the flow is practical using this method. The scale factor of a sensor can be quantified empirically or predicted using a model. In these tables, we provide the numbers. We are quite sorry that we can't compare here on board another one, but those are the numbers of the sensitivity that we measured. So the order of magnitude differences between the prediction and the experiments implies that the heat transfer correlation should have been taken more carefully by analyzing the flow in our test rig better, maybe. So in this work, we showed a novel sensing principle based on the static buckling of a double-clamped thermal actuator. The results provided by a reduced order model were consistent with the experimental data, proving the sensing concept. In addition, we showed the role of the direction of the flow over the response, and the results show quite interesting insights on the opportunity to really measure the flow direction. Last, some numbers of the sensitivity of the devices that were operated in our test rig. To conclude, I'd like to state some of the most important advantages as we see them. First, the devices exhibit very high sensitivity even before optimization. The versatile mode of operation of the sensing of the elementary sensing block was very important if one would like to measure the flow of the velocity of, or the wall shear stress, of course, if installed in the wall. And last, and maybe the most practical important one, is the simple yet elegant model design and fabricational process of our sensor. Thank you very much.